All right, so first thing I want to do is kind of talk. Now, I know sports analogies for things aren't always great because not everybody is a sports person. I get that. But I think one of the kind of the best analogy for what we're going to work with right here is a sports analogy. So what I'm going to do here is draw a football field.
I don't get it.
Shut up. All right, so there's the end zone right here. Okay. So we have to cross this line here with the football to score a touchdown, Jackson. We go with that? Okay. So a football field is broken up into increments of 10 yards, right? So here's 10-yard line. Okay. Halfway would be the 5-yard line. Okay, so for those of us that don't know football, okay, there are penalties, right? So if I break the rules of the game, then the other team gets yards added to where they're at. So let's say that let's say that I'm on like the 40-yard line. Okay, and I'm the offense, so I'll just say O for offense. And we're going this direction. We're going towards that end zone. And let's say the defense, which is on this side, let's say they break the rules of the game. Well, what's going to happen is that the offense then gets rewarded with yardage. So they get to move the ball closer to the end zone. So there's penalties of 5 yards, 10 yards, 15 yards, and then there are some penalties that the ball gets placed where the penalty happened. So if, let's say the defense makes what's called offsides. So before the ball is snapped, a defensive player jumps across the line and it gets closer to the quarterback, right? That gives them an unfair advantage, so they throw a flag. And what happens is that now instead of at the 40-yard line, we get 5 yards closer. We put the offense there, put the defense there, and now we're going to play from there. Does that make sense? Okay. Now, we can keep doing that, but what happens eventually, if I'm on the 10-yard line and there is a penalty that is worth 5 yards, I will go to the 5-yard line. Okay? But if I'm at the 9-yard line, let's say the offense is right there at the 9-yard line. Okay? If I have a penalty that is greater than half the distance to go to score. So right now the distance to score is 9 yards, right? Half that distance is 4.5, right? If I have a penalty that is more than 4.5 yards, they will not give me the whole penalty. Okay? So if I'm at the 9-yard line and there's offsides, they're going to give me half the distance to the goal line. Okay? So they're going to take the ball and they're going to move it to the 4.5-yard line. Does that make sense? Okay? Now let's say let's say the defense just keeps jumping off sides. They keep making this 5-yard penalty. Okay? Which now from that 4.5, they're going to say, well, half the distance is 2.25, right? Okay? And the reason they're doing this is because I'm at 4.5 and they enact the whole 5 yards. Touchdown. It gave me a touchdown. So the penalties, the rules, will not generate points for a team, right? So what they do is they'll say, we'll go half the distance. Okay, so now we're at the 2.25. They jump off sides again to get to the, now 1.75. Okay, or I guess 1 point, whatever. Okay, not 75, but whatever. So half the distance, right? And we keep doing that. If they keep jumping off sides, they always get closer and closer and closer by half the distance to go. Will they ever touch the goal line? No. If they never touch the goal line, mathematically then, the goal line is a what? If you cannot touch it. Not a limit. It's an asymptote. Okay? Does that kind of make sense to everybody? Okay? Now there might be better analogies out there, but that's the one that kind of rings true to me. When we talk about rational functions, and the reason I bring that analogy in is because rational functions are governed a lot of times by asymptotes. That is one of the main things that we have to think about when we're working with rational functions. A rational function is simply a function that is generated by taking two polynomials and dividing them. Okay, and they can be, your polynomials can be anything. In the last class we just took a handful of different polynomials and looked at what they generate when we divide them. What happens is polynomials standalone are what we've been working on for a majority of this course. So if I have something like x squared plus 5x plus 6, okay, we know what that looks like. Okay, if I have a, let's do a cubic, that is x to the third minus 2x squared plus 2. We know what that cubic looks like. Okay, those things by themselves are polynomial functions. If I take f and I divide it by g, which is just taking this top function and this bottom function and dividing them, right, in that order, the result is this graph over here. Really looks nothing like what f and g themselves look like, right? Okay. But what is happening, if we think about this, okay, if I take, I know it gets messy here, but if I take, let's take an x value of -1. Okay. If I take -1, f of -1 is that number right there. G of -1 is that number right there. If I divide them in that order, 2, because that was the numerator, divided by -1, which would be -2, right? Does -2, so if x of -1, does that give me, is that -2 realized right there on that graph? Does that make sense? Okay, so what's happening when we do this is we're taking the y values off the orange one or red one, divide them by the y values off the purple one, and when we do that, that quotient is realized by this gray one. Okay, and if we do that at all of our x values, then we get this complete gray curve. Okay, now there are some values that are problematic here. Okay, let's do this real quick. Let's do complex root of g of x. Okay, so this number right here, -0.83929. That number, and I might be able to do this a little bit better. Nope. That number right there, okay, it's irrational. It's incorporating some radical, which is this point right there, okay, is a number that would be it's a 0 to this. Does that make sense? Okay. Well, if it's a 0 to that, that's where that graph crosses the x-axis, right? Okay. So it's a 0 to that. But when it becomes, so if I plug in 0.83929 right here in this denominator, it's going to give me division by 0, right? Well, that's a problem. Division by 0 cannot happen, right? We're not allowed to do that. Therefore, our graph should not be plotted here. Does that make sense? We cannot have a point plotted on any x value that has a -0.83929 value. So there is what we refer to as a vertical asymptote that is going through that point right there. Does that make sense? Okay. And if that we have that vertical asymptote, I don't know if I can do this. Yeah, I think so. Maybe I can do this. Nope. Can't. Okay, so to the left of that asymptote, our graph is going to get closer and closer to it, but it'll never cross it. Does that make sense? To the right of that asymptote, it should be right here, our graph is going to get closer and closer to it, but it's never going to cross it. It's kind of like that football never crossing that goal line. Okay. But that is, those asymptotes are kind of what is structuring this graph. There's another asymptote here I guess not. Not another vertical one. There's a horizontal asymptote. If I move further and further out this direction, okay, this graph will never cross the x-axis. Does that make sense? As I move this direction, now we do cross the x-axis here at -2, which is okay, and we'll talk about that later on. You can cross horizontal asymptotes, but a horizontal asymptote for the main purpose is to identify what is happening as x gets really, really, really big. So it's talking about the end behavior. And as I look at the end behavior, we can see that the graph starts to get closer and closer to that asymptote as we move further and further to the left. Does that kind of make sense?
Yeah.
Jimmy?
So you're sometimes allowed to cross the horizontal asymptote, but never a vertical one.
Yes, you can never cross a vertical one, because a vertical one is generated through realizing domain restrictions because divided by 0. If we were to cross a vertical asymptote, we're saying then that there is a y value that is generated when you divide by 0. And we know that that's contradictory. You can't do that, right? So crossing a vertical asymptote is an impossibility. You're not allowed to do it. Crossing a horizontal asymptote is allowable, and it happens generally very close to the origin. Okay? Now that's a relative phrase, because close to the origin could be, depending on what your coefficients are, it could be like 100, or it could be, like in this case, -2. That's relative to the size of your coefficients. However, if we do cross, there's going to be steps for developing all this information that's going to structure these graphs. One of those steps is to realize, does my graph cross the horizontal axis, horizontal asymptote or not, which a lot of times is the horizontal axis. So there's not going to be any guesswork in whether we do or we don't. We'll have algebraic approaches to it. So that's one thing. We can look at these graphs in a different order. We looked at f divided by g. If I look at g divided by f, that's a completely different graph. Okay, kind of weird looking, right? Okay, and in that case, we're going to have what we call an oblique asymptote. What's happening down here is that the graph is, in the long run, approaching some values, but that y value that it's approaching is going to be determined by the equation of some line. Okay, and basically, now here's where our previous information is going to come into play. That asymptote that is being realized here, which is what we call a slant or an oblique asymptote, is actually generated by the long division algorithm that we did in section 3.4. Okay, the equation of a slant asymptote, and we'll talk about this in greater detail later, but the equation of the slant asymptote is actually the remainder of the long division. Okay, but that's something that we'll get to later on. But my whole purpose here of showing these is just to get you to realize the functions that we've seen in the past. We have an idea of what parabolas and cubics and quartics and those types of things look like. You probably have a very limited understanding or exposure to rational functions. They look drastically different. Okay, and the patterns for them, there are patterns that exist, but it's, if somebody were to ask me, what is, and I've been doing this a lot longer than you have, what is the general pattern of that? I would not know that it looks something like this, right? I would have to go through kind of the analytics of it to recognize that and realize it. So, like if I give you something like this, y equals 2x squared plus 3x minus 7, you have a general understanding of what that looks like, right? A parabola, concave up, y intercept -7, okay? But if I were to give you some random rational function with very limited exposure to them, you're not going to have that kind of foundational information. Okay? So let's get into this stuff. A rational function is a function of the form r of x equals p of x divided by q of x. So r of x equals p of x divided by q of x. So what we say is that p of x is some polynomial. It can be any polynomial that we could ever imagine. Q of x is the same. It could be any polynomial you could ever imagine. Okay. Usually we want them to be different because if they're the same, they just give me 1, right? Which is a pretty boring graph. What we're going to argue here in the definition is that P of x and Q of x have no factors in common. So when I factor P of x and I factor Q of x down to their linear factors, neither of them have like x plus 1 and x plus 1. And neither of them have like x minus 2 and x minus 2. Okay? So they have nothing that is shared factor-wise. Okay? It says their graphs look quite different than the graphs of the individual polynomial graphs. It says that the domain of a rational function consists of all real numbers except those for which the denominator is 0. Okay, we know, and this is trying to give you guys a little bit of an understanding of why we've done some of the things we've done in the order that we've done them early on in the year. If you guys remember the domain stuff, I'd ask you to look at domains and look at a graph and tell me domain and range. You look at a function, and this is one of the things that we actually struggled with. Look at the function and determine what is the domain from the function. Well, we had the square root ones, which we'll come up and talk again and in the next couple of chapters, but we also had division. We had rational functions when we were talking about domains. And the number one issue was, where does the bottom equal 0? Because that is going to be a domain issue. And that essentially, when we were doing that back in September, that was laying the groundwork for finding asymptotes today, or for today's stuff. Okay? So if I gave you something like, f of x is equal to 3x squared plus 5x over x minus 2, and I asked you, where is there a domain issue? Well, we have division by 0, so x minus 2 cannot be 0, so x cannot be 2, right? And the reason we were doing that, let's graph this real quick. If I take, I know you can't see it yet, but okay, so if I graph that, we get this here. Back to standard view. Let's change the zoom on the y-axis. So we get something like this, and the idea is x could not be 2. So if I put in x equals 2, we have that thing right there, and that red line is a what for us? Yeah, it's an asymptote. As I look at that red line compared to the curve is always, as I look at the positive y values, that curve is always to the right hand side of that asymptote, right? No matter how far I zoom out and then scroll up, no matter what x or y value I want to get to. So let's say I want to get to 9500. If I zoom in far enough, and as long as GeoGebra has the calculating power, the available RAM to do this, you will eventually see that around 9500 is there still separation between the asymptote and the graph. Yeah, no matter what number you go to, that's the idea of an asymptote. No matter what number you're going to go to, this curve is going to be to the right of that dotted line. Now, as we look here and we scroll down this direction, you're going to see that the graph is always to the left of that dotted line. Does that make sense? But this part of the graph will never ever cross it. This dotted line is telling us that is where division by 0 happens. And if it's division by 0, we know we can't evaluate there, right? So we draw those in graphically to remind ourselves that that division of 0 is what is going on there, and you cannot, because the division by 0 is undefined, you cannot yield a defined y value to plot an ordered pair on that dotted line. So that's something that we're going to kind of use now. Okay, we've learned how to do it. Now we're going to put it into practice. So when graphing a rational function, let's pay attention to the behavior of the graph near those x values. So really what we're going to be interested in is first identifying the zeros of the denominator, and then analyze what happens really close to that zero on the left of it, and then what happens really close to that zero on the right of it. Okay. Essentially, if I were to evaluate my function at values very, very close to that 2. So let's say I evaluate at 1.99, and then 1.999, and then 1.99999. What is happening to those y values as I evaluate closer and closer to 2? And then we'll do it on the other side too. 2.01, 2.001, 2.0001, and see what is the pattern that's happening with those y values as I get closer and closer to that 2. And that will tell me then whether, basically what's going to happen, you're going to have two options. Either your y values are going to get really, 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 really big in the positive direction, or they're going to get really, 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 really big in the negative direction. Okay? And that's how asymptotes, vertical asymptotes operate. Okay, and then here's kind of a really a simplistic explanation of just that. If I take a function f of x, which is 1 over x, okay, that is generally referred to as our parent function for rational functions. Okay, they actually refer to this as the reciprocal function. That's the reciprocal of x, right? But it is a rational function. What can x not be here? X cannot be 0. So if I'm going to graph this thing, what we're going to do is the first thing we would come through is that we would put a vertical line through x equals 0. Oh. And obviously this is going to be like your preference. I like to make them dotted lines. But that's just going to remind me that I'm not allowed to put an ordered pair on that line. Okay, because that's where division by 0 happens. Now, what we're saying here is if I plug negative 0.1, because I'm interested in what happens close to that asymptote. So if I plug negative 0.1, would you guys agree that that's close to 0? Okay, it's on the left-hand side of 0, right? If I plug negative 0.1 in, so it's going to be equal to 1 divided by 0.1. Well, that's 1 divided by 1/10, right? Well, 1 divided by 1/10 is 10. And in this case, because the x was negative, that's going to be negative, right? So I get the ordered pair of negative 0.1, negative 10. Okay? Now if I go to a value that is even closer to that asymptote, okay? So that is 10 times closer to the asymptote than what 0.1 was, right? Okay? So now I'm going to have 1 divided by negative 1/100th. Well, 1 divided by negative 100th is negative 100, right? So I have the point negative 0.01, negative 100. What happened comparable that number to that number, relatively speaking? As the x's got closer to the asymptote, these numbers did what? Got more negative, right? Got bigger in the negative direction. Let's see if that happens again. If I go negative 0.001 as my denominator, okay, oops. So that's going to be, and it's not this one here, but that's going to be 1 over negative 1,000th, right? Okay. So is that going to give me then negative 1,000? Is that more negative than what the other two were? So as this number is approaching this one, as my x values are getting closer and closer to 0, approaching 0, okay? In this notation right here, you're going to see this quite a bit as we move on. That negative superscript right there, and it's kind of hard to see, but there is a negative superscript right there on that 0. It's approaching 0 from the left. That's what that negative sign does, or tells me. Okay. And hopefully that makes sense as we look at those x values. Negative 0.1 starts all the way to the left. Negative 0.01 moves a little bit more closer towards the right. Negative 0.001 gets closer to the right, right? So it's moving from the left. Is it okay with everybody? As we're moving from the left, the y values, the closer and closer I get to that zero, that asymptote, these y values are getting more and more negative, right? Well, if I get to like negative 0.000000000, say like 1,000 zeros and a 1, this number is going to be very, 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 very big, but negative, right? So as these values are approaching the asymptote, these values are getting bigger and bigger in the negative direction, so these are approaching negative infinity. Does that kind of make sense? And that's why when we approach a vertical asymptote, we have one of two behaviors. And it's basically because we're either dividing by a negative number, so you're taking like a whole number like 1 and dividing it by something very, very small. Because that the closer and closer we get to that asymptote, we're divided by something very, very small. So a positive number divided by a very, 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 very small positive number is then a huge positive number. Does that make sense? Okay. Or a negative number divided by a very, 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 very small negative number is also something very, very huge. Or a positive number divided by something very, very, very small that is negative. A positive divided by negative is a negative, so it would be a very, very, very large negative number. Or if I take a negative number and divide it by a very, 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 very small positive number, that is still going to yield a very, very, very large negative number. So you've got two options, positive infinity or negative infinity. And in this case, when I look at x on the left-hand side, so right now, I'm just going to type in, like if I chose, if x is between negative 1 and 0, what does 1 over x look like? Not yet. So this right there, and we'll make it blue. So that blue graph right now is choosing like an x value of negative 1 and plugging it in here and seeing what I get. Well, when I do that, it's going to give me that point. Let's put a point. It's going to give me close to point B. I don't know why I can't scroll all the way up there. But if let's say I chose negative 0.87945 and I plugged it in here, it's going to give me that y value right there, correct? Now, if I chose x to be like negative 1/10, it's hard to, just one little slight movement with my cursor drops this thing very far. Close enough. Pretty close to negative 1/10, and you see that gives me pretty close to negative 10, right? Now, as I keep moving down, no matter what values I choose for x, when they are closer and closer, okay, so that value right there, let's put a point on there, attach D to that. Oh. All right. The thing with this is that sometimes, because I'm zoomed in so far, it won't let me really get the point that I want. But if I were to plot that point right there, okay, you're going to get a number that is very, very, very small here. And this is obviously going to be down by negative 80 something. Okay. But you're never going to be able, on this left-hand side of this asymptote, that blue curve is never going to jump through that dotted line, right? Does that make sense? Okay. Now, as I work to the left, okay, so we went from negative 1 and started evaluating from negative 1 up to 0. Let's go this direction. Okay, what if I get negative 2? If I put negative 2 in here, what do I get? Yeah, negative 1/2. Okay, what if I try negative 3? Negative 1/3. What if I try negative 10? Negative 1/10. What if I try negative 100? negative 1/100th, right? Okay, now those are all points that I'm gonna realize here, but think about the y value. Will I ever get the y value to be 0? No, because you're always going to have 1 divided by something, right? Okay. And the idea is, if I have an object, I should be able to divide that however many times I want to and still have that object, parts of that object, right? Okay. So I'll never be able to get it to go to 0. It's never going to vanish. Okay. So then when I graph to the left of 0, the rest of that graph ends up looking like that. So what does my x-axis, if I go all the way out here, let's say we go out to negative 260, is my red curve still below my x-axis? Yeah. So what is my x-axis playing as we move further and further to the left? What does it be? It's acting as an asymptote. Okay, and that we don't cross it. Okay, so now the exercise is to do the same thing on the right-hand side of 0. Okay, so if I'm on the right-hand side of 0, yeah, so now we're just going to, if I choose 1, it's 1 over 1, right? So it's a positive number. If I choose 1/2, it's 1 over 1/2, which would be 2. If I try like 1/3, it's 1 over 1/3, which would be 3, right? If I try 1/10, it's 1 over 10, which would be 10. If I try 1/100th, which is really close to 0, it'd be 1 over 1/100th, which would be positive 100, right? So as we go from x being less than 1, and I graph 1 over x, it's going to give me that. Okay, because of the way that we're dividing a positive value of 1 by a very, very small positive value. It's positive divided by positive, so my result should be positive. But 1 divided by a very, 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 very small amount is actually a very, very, very large amount, right? Okay. Now, if I move to the right here, okay, take 1 and divide it by 2, I should get the point 1 comma 1/2, right? Oh, sorry. Should be 1 comma 1/2. So x was 2. So it should be 1 over x, which would be 1 over 2. Okay. So then if x is 3, it'd be 1 over 3, right? If x is 4, it should be 1 over 4. If x is 10, it should be 1 over 10. And we're starting to see then that in the long run, does that graph start to approach the x-axis but never get to the x-axis? Okay. So this is the structure, and it's kind of a watered down analysis of how our graphs, every rational graph, behaves near asymptotes that are vertical and how it behaves near asymptotes that are horizontal as x gets really large in either direction, positive or negative. Is that okay? All right. Let's see here. I'll let you guys, so you guys got these notes, I'll let you read this paragraph, but I'll explain to you what that is saying. We talked, and I've already heard somebody say it about the phrase limits, which is where this stuff is leading us. If that's my asymptote right now, okay, the reason that we have what we call discontinuity here. Okay, we have an asymptote. It's discontinuous. If you remember back to the beginning of chapter 3, we said that a graph was continuous. It might have been chapter 2, actually. The end of chapter 2, maybe. It says a graph is continuous if you can place your finger on any part of the graph and you can trace that entire graph without lifting your finger. That was kind of our layman's phrase for continuity. Okay, this graph does not allow you to do that. If I place my finger here and I trace it, my finger is going to go down to negative infinity. But to get back up to this other branch in the first quadrant, I've got to lift my finger off the current part of the graph and bring it up here, right? So we're discontinuous at that place that I have to lift my finger. Now, that's kind of a bad, like mathematically speaking, a bad definition because there's no math there. Mathematically speaking, we determine continuity at these positions where it's called a limit, if I put my finger there and I put my finger there, my interest is going to be what happens at x equals 0. So what I do is I move my finger towards x. I keep it on the graph, but I move my finger towards x being 0. Does that make sense? And in this case, on the left-hand side, my finger is going to go down to negative infinity, correct? Over here is my right-handed finger, and I'm going to move that towards 0, keeping it on the graph, though. And my finger is going to go up to positive infinity, right? My fingers diverged, meaning they did not come together, right? When they do not come together, that means you have discontinuity here. It means your point or your function is not defined there. Does that make sense? So you either have a hole or an asymptote there. Okay, in this case we have an asymptote. When we talk about this idea, we use these superscripts of a plus sign on that 0 and this negative sign on that 0. Those superscripts are read as approaches from the right. So that plus means I'm coming from the right. Okay, so it'd be the idea of my finger being right here, and I'm approaching 0 from the right. Does that make sense? I'm asking myself, what is my y value doing? Here, this negative says you're approaching 0 from the left. Okay. At this stage right here, let's say we had -1. That's the x value. As I move from the left, is my y value, is this finger here, matching up to this finger here as I move to -1 from the right. So what that would tell me is that that graph is defined at -1 because we have essentially what we call a limit at -1. It means there's no hole, there's no asymptote there. Does that make sense? Okay. And we'll talk about, I may have misspoken there a little bit about a hole because of a limit, but we can still have limits at holes. We'll talk about that later on. But the idea is that in an asymptote, you're going to have discontinuity. Okay? And we'll pick up from there tomorrow.